Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about common ion effect. Basically, I've split the topic over two videos, so it's a two-part series. Here in the first part, I would like to talk about a bit of the theory behind common ion effect. And in the second part of the video, I would like to talk about the calculations that are based on it. Okay? So if we're going to talk about common ion effect, what we probably should talk about first is the attempt to dissolve a solid that really doesn't want to dissolve in water. Okay? So let's say that we want to talk about silver chloride. Okay, so if you have a pile of silver chloride, a lump of this solid, and you have a beaker of water and you throw it in, the majority of the silver chloride will sink to the bottom and sit there as a solid lump, right? It doesn't like to dissolve. But a very small amount of it will break up and dissolve. So a very small amount of it will break up to give you silvers and chlorides. Now, when they break up and they start mixing with the water, these would both be aqueous. So aqueous and aqueous. The charge on a silver is 1 plus. The charge on a chloride is 1 minus. And if you break up one silver chloride, you would get 1 silver and 1 chloride. Now, for this thing here, it is considered to be an equilibrium, because for every 1 silver chloride that breaks up and becomes dissolved, there will be a silver and a chloride that's already dissolved that will come back together to form a solid. So simultaneously, you have some of the solid breaking up, and you have some of the broken up ions coming back together. So this will be an equilibrium. Now, these compounds really don't want to dissolve in water. So we're talking about extremely low amounts of silver plus and extremely low amounts of Cl minus. Now, the really neat thing about solutions is that you can attempt to dissolve more than one thing in the same container of water. So if I wanted to, I could throw in, say, some sodium nitrate. Because the chemicals in sodium nitrate are completely different from the chemicals in silver chloride, the two of them will act independently, right? The amount of silver chloride that guy can dissolve will be completely independent of the amount of sodium nitrate I can dissolve, right? The two of them just have nothing to do with each other. But if I attempt to dissolve something that has something in common with what I already have, then I get the common ion effect. So let's say instead of trying to dissolve sodium nitrate, I try to dissolve some silver nitrate. Now the problem arises because I've already dissolved a whole bunch of silver from the silver chloride. And now I'm attempting to dissolve more silver from the silver nitrate, right? I have a second source of the same ion. As long as the two chemicals were completely different, then they acted completely independent of each other. But the minute that you have an overlap between the two, then they're going to interact. Because the amount of silver coming from this and the amount of silver coming from this, there is a maximum, so there's going to be a limitation on both. And what ends up happening is that if you attempt to dissolve a second chemical that has an ion in common ion, you're going to decrease the amount that you can dissolve. Okay, the amount that's dissolved is going to be much lower. So common ion effect always leads to a decrease in solubility of the ionic compound due to the addition of a second compound with an ion in common ion. Now I have an example here. I was talking about lead 2 chromate and lead 2 nitrate. Because they both have lead 2 in it, the lead 2 plus would be the common ion. Now it doesn't always have to be the cation. It could be the anion, right? So I could talk about silver chloride and I could talk about sodium chloride. Because they both have chlorides, that would be the common ion. So this happens whenever you have two compounds, and that's one of the ways that you can kind of get a feel that this is the problem you have. This type of problem will talk about two different compounds, but they will have something in common. They'll either share the same anion or they will share the same cation. Okay, cations and anions. Now, the reason why you get a decrease in solubility is because of Le Chatelier's principle. Okay, and I've got an example here. So if we talk about the lead-2 chromate, lead-2 chromate hates dissolving in water. It really doesn't want to dissolve. But a small amount of it will dissociate. A small amount of it will break up. So if you've got lead-2 chromate, you get some lead-2 pluses and you get some chromates. Okay, ignore this extra beaker for a minute. This is an equilibrium. It does take a little while for the leads and the chromates to dissolve, so it does take a while for the equilibrium to establish, but what you'll end up with is this has dissolved the maximum amount of lead-2 pluses and the maximum amount of chromate 2 minuses. Now what you're going to do is you're going to mess with it. You've got a beaker with a related chemical, okay? They both have leads, but the anion is different. This has a chromate, this has a nitrate. Now the trick is the second chemical loves water, right? First one hates water. It's very hard to dissolve, but the second one loves water. So if you put lead-2 nitrate in water, it breaks up like 100%. So this beaker here has lots and lots and lots of lead-2 plus, like a massive amount. So if you think back to Le Chatelier, now, if you're having some trouble with Le Chatelier's principle, I do have a video on Le Chatelier's principle, so it might be a good idea to perhaps pause here, watch the video on Le Chatelier, and then come back and finish, okay? So Le Chatelier says, if you add extra of any chemical, the equilibrium will attempt to react to reduce it. Okay, your equilibrium will always work against you. So if you're adding extra lead-2 plus, the amount of lead-2 plus is going to go up, this equilibrium is going to react to reduce it. And the way that it's going to react is for a little while it stops being in equilibrium and it's going to run backwards. Because going backwards takes the extra lead, takes the chromate, puts them together, and turns them into lead chromate solid. Right? So by going this way, you're going to use up the lead-2 plus. Because using up the lead-2 plus will make lead chromates. Now, unfortunately, it will also use up some chromates, right? It'll use up the leads, but it also uses up chromates. And it will make more of the lead-2 chromate, right? So it's going to mess with everything. But what it does is by going backwards, it reduces the amount of lead-2 plus. And if you reduce the amount of lead-2 plus, that counteracts the increase that you did, right? Le Chatelier is all about counteracting. So for a little while, the whole thing goes backwards until eventually all the levels equal out and then it becomes an equilibrium again. But if you're going to run this reaction backwards, that means you are going to be making this reactant, this solid. So what will happen is your beaker will be here. You will have dissolved a whole bunch of this, so most of it will be on the solid on the bottom, but a small amount will be dissolved into liquid. You add this second chemical, and all of a sudden, magically, poof, a precipitate forms, right? You're going to end up with a huge amount of solid just magically appearing because you're making the equilibrium run backwards. By making it run backwards, you are producing extra solid. So if you're producing extra solid, when it appears in solution, that's what we call a precipitate, okay? And that's why the solubility is going to go down, right? Because you're forcing this reaction to go backwards. You're forcing things that used to be dissolved to turn back into a solid. So you are decreasing the solubility, okay? That is the common ion effect. So like I say, I went through the equilibrium part here a little quick. If you are having trouble with Le Chatelier's principle, you really should go back and take a look at that other video. So once again, I'd like to thank you for visiting me here at Chemistry with Dr. Clark. And I encourage you that if you have to do calculations based on the common ion effect, that you take a look at part 2 of this series.